recognized for a long time now that the manned orbiting space platform is a major step towards developing the nation's total space capability, whether for scientific or military purposes. We've also recognized that we can't develop such a vehicle without a thorough understanding of the disciplines and technologies that contribute to it. The test you've just seen is only a small part of the Space Station Research and Development Program here at Astronautics. Behind the scenes is a wide range of activity that's been underway since 1959. At that time, I directed Astronautics to start the necessary programs of research and, where possible, development to prepare itself to adequately serve the government in this field. This is a progress report on part of that work.
Our space station program is partially based on the hard experience acquired through conception and development of the Centaur space vehicle, the Aaron's 24-hour orbit environmental test satellite, Atlas scientific passenger pods, and the Azusa tracking systems. But the philosophy of concurrency has led us to pursue continuing studies of the man-machine systems which are now on the verge of reality. Our conceptual designs have changed as our knowledge has become more sophisticated on the one hand and more practical on the other. The evolution of these ideas relates to the evolution of science as we and others have influenced it, and this is apparent in concepts ranging from two-man space labs to eight-man ships for flights to Venus and Mars. But design studies, operational analyses, and theoretical investigations are only the beginning. To verify designs in the laboratory, to breadboard and operate critical components and subsystems, to probe for advancements in the state-of-the-art, to give substance to theory with physical tests is to advance a concept toward a logical working system. This, then, becomes the space station program.
Here at Astronautics, we have put our facilities and talents to work to research and develop the electronic, mechanical, structural, and crew systems for manned space operations. Since the space station is primarily a test lab to be tracked and controlled in orbit, a worldwide tracking net will be required to establish a station ephemeris and to program the trajectories of its support vehicles. Tracking system requirements are being established by personnel who developed Azusa Mark I and II and are now building the GloTrack Global Tracking Network. Space station systems design must consider the balance between onboard data processing and the communication of that data to the ground, as it would influence bandwidth requirements, weight, and power consumption of onboard equipment. These and other problems are being solved by a team which has placed one of industry's largest high-speed data processing centers into operation. Before we design its guidance, control, and display equipment, techniques to assemble and supply a spaceship in orbit will be well understood. Here in our computer labs, simulated rendezvous and docking operations have been underway since 1959. This simulation is expanding our knowledge in the development of control systems, autopilots with proper characteristics, and cockpit displays. In a more advanced setup, models illuminated by point sources of light against celestial and Earth backdrops add to our understanding of visual phenomena in space and the design of television display equipment. Space station dynamics are, of course, under theoretical investigation, but these studies are being supported by a program of attitude control simulations with our coast phase test stand. A 3-ton balanced mass supported by a friction-free air bearing duplicates the motion of a vehicle in space when directed by rocket, autopilot, and other orientation equipment. Although Astronautics built the stand for tests of Centaur's attitude control systems, experience here is being directly applied to the space station program. Another application of knowledge acquired from our work with Centaur is in the field of zero gravity. The phenomena defined during our investigations of weightlessness have a direct influence on space station design and on the development of devices to control the behavior of cryogenic and other fluids in a space environment. We come now to the problem of designing a structure not only for crew and equipment support, but for protection against the space vacuum, against various types of radiation, and against meteoroids. Analytical solutions to space vehicle heat transfer problems are substantiated in our space environment simulator. Here, we subject an entire satellite to a vacuum of 5 times 10 to the minus 7th millimeters of mercury, equal to an altitude of about 150 miles. Cold walls and a solar source complete the space environment simulation. Astronautic scientists have been investigating the extent and effects of solar, Van Allen, and man-made radiation since 1957. Instrumented balloons, radiation facilities at General Dynamics Fort Worth, and General Atomic, and the ion accelerator at Astronautics have all been used in this work. The deadly protons and electrons in Van Allen and solar radiation demand a special understanding of the methods and materials to shield against them. Nuclear physicists at Astronautics are using a linear accelerator capable of bombarding a specimen with 3 million volt particles to establish space station shield criteria. Equally important is the meteoroid penetration problem and the development of puncture-proof vehicle structures. This is a recovered part of MA7, the John Glenn Atlas booster. Hundreds of microscopic craters on this and other fragments were apparently caused by meteoroid impact. Our studies indicate the existence of meteoroids in substantial quantities at relatively low altitudes and demonstrate the need for adequate protection techniques. In support of our investigations, typical samples of a space station structure are being subjected to high-velocity impact tests, both with and without vacuum conditions at Astronautics Green Farms facility. From these tests, meteoroid shield designs are being established for the space station program. To measure the effects of long-term vacuum on proposed space station materials, we seal the specimens in a vacuum at 10 to the minus 8th millimeters of mercury for as long as 15 days. Our purpose here, of course, is to determine what changes, if any, will occur in the properties of materials and lubricants. Since weight is a major determining factor in spaceflight capability, Astronautics is attempting to develop light and extremely rigid structures. Our engineers are engaged in research and testing of the frame and stringer stiffened concept as applied to space station construction. By exploring the general compression instability regime, we can design space vehicles and payloads of minimum structural weight with maximum structural reliability. This particular specimen, incidentally, weighs only 6 pounds and supported 6,800 pounds before failure.
The human element is viewed by astronautics as critical in dictating design criteria for manned space systems. And we anticipate a trend which will constantly increase the need for comparative analysis of the interface between man and machine. Our life sciences programs and facilities are designed to achieve 2 major goals. First, systems integration affected by interdisciplinary bridges between the soft and hard sciences. And second, an increased capability for qualitative and quantitative definitions of human performance measured in units compatible with engineering equations. This facility represents a centralized general dynamics capability, which will also support the studies of other divisions. Here we have a closely knit team of physicians, psychologists, biologists, and engineers concerned with first-order man-vehicle interface design. In our biochemistry lab, for instance, we're devising a miniaturized kit that astronauts will use to check both physical condition and ship's environment during a mission. Designed for compatibility with weightlessness, the kit is equipped for blood and urine sampling, bacterial and particulate contaminant studies, and other necessary tests. In the physiology lab,
we're working on instrumentation techniques to be used by physicians in determining the astronaut's condition during tests in our space station simulator. Such techniques may eventually be applied to biomonitoring via telemetry when a station is in orbit. To support our rendezvous and docking studies, human factors personnel are probing space visibility phenomena using models with various shapes and surface coatings. A collimated light beam in a black void makes the spacecraft appear as it would under sunlight in space. But this is not its true shape. We're hoping to develop a surface coating to solve what could otherwise be an orientation problem for the pilot. Operator performance, observed by psychologists through one-way glass and measured by external recording equipment, is under study for a broad range of future applications. This subject is working with Logit, a logical inference tester, which evaluates and records skills in reasoning, memory, and decision-making. Radar, a response analysis tester, is used for sensory motor matching tasks where the subject's speed and accuracy are recorded. These devices will serve as interface design guides through evaluation of psychological stress factors associated with proposed space crew tests. Transat, a translation and attitude tester, is being designed to help us explore that critical set of variables, the quick exchange of operational information between man and machine under any conditions. When the vehicle displays its operational status to the pilot, his sensory ability to process the data for fast and efficient feedback can be determined and improved by the use of this equipment. But our purpose is not simply to measure man's level of tolerance and response to stress. Placing a crew in the loop in a near prototype, realistic breadboard of working hardware is the ultimate test and the definite bridge to early space operational capability. At the time we put this full-scale mock-up into operation, there were no available data on three-man orbital simulation testing. Now it will be possible for a crew to experience most of the operational events from launch to landing. And now we can establish guides to hardware design and develop personal equipment, crew logistics, and crew training requirements. When connected with the IBM 7090 computer, we can simulate flight noise and vibration, couch and pressure suit restraints, and all biological environments of orbit except hard radiation, zero-G, and launch or re-entry hypergravity. Pressure suits, helmets, integrated seats, and restraints follow the design expected for actual flight. Incorporating dynamic control and display equipment, the launch and re-entry vehicle serves as sleeping quarters during orbit, and because of the three-man crew size, is always inhabited by one of the astronauts. The second module contains the environmental control, food, waste, and sanitation equipment of the life support system. The shirt sleeve environment, with sea level, atmospheric composition, and pressure, is completely controlled by the crew from within. Part of the flight simulation includes emergency procedures to counteract environmental contamination and cabin decompression. The research module above includes displays, controls, communication, and recording equipment. In August 1962, we successfully completed a 30-hour test under simulated orbital conditions. In long-duration tests, ranging from several hours to several weeks, crew members will live on space rations and maintain normal rest, work, and recreation cycles.
These then are the beginnings of the manned space station program at General Dynamics. They necessarily include analysis, design, experiment, and verification across a broad range of technical and scientific disciplines which we could only sample here. It's a continuing program and a challenging one. Our efforts are geared toward meeting that challenge.